Hi. This presentation discusses the description of a capstone project proposing the development of a simple CPU. At the end of this presentation, I hope that you will be able to explain the functional requirements proposed, which address a simple CPU architecture to control a small card, and to plan the main tasks needed to develop a solution. This presentation will start with the overview and requirements, followed by a list of tasks, and to close we will look into possible expansion directions. Let's then look at the overview and requirements. This is what the small card looks like seen from above. You can see that it comprises two side wheels driven by independent stepper motors and one servo motor that is able to drive a pen up or down so as to enable the card to draw a line when moving. The onboard electronics comprise the BASIS 3 board and eventually additional driving electronics that you may consider necessary. Basically, what you are asked to do is to develop a simple CPU architecture that is able to execute a small set of instructions created to control the card actions. The inspiration for this work was the Logo language designed many years ago, which is frequently associated with teaching children to code. You may show that your implementation works by using the BASIS 3 board to control the small card. Servo motors are simpler to control, although it may take some digging to find the appropriate information. So I'll just say a few words about the stepper motors used to drive the side wheels. These stepper motors have four phases that may be driven as represented in this slide. You may notice that successive waveforms are in quadrature, 90 degrees out of phase. So the third waveform is just the complement of the first, and the fourth is the complement of the second. Wikipedia and many other web sources offer plenty of information with this respect, so it shouldn't be difficult to learn more about it. Anyway, basically what you have to do is to generate a set of waveforms like this for each motor, and be aware that changing the quadrature will cause the motor to rotate in the opposite direction. You may also anticipate that part of your CPU instructions are meant to generate these waveforms. And here's the first part of a table that summarizes the set of instructions that you are asked to support. I won't describe them one by one, since their meaning is pretty much straightforward. Most important among them are, of course, the movement control instructions: move front, move back, move left, and move right. The second part of the table is shown in this slide. You are, of course, invited to add any instructions of your own choice if they come to your mind. What are the tasks? As usually, since we are implementing the CPU as an FSMD, you have to start by designing the data path architecture. For simplicity, you may assume the same 8 bits width for the data bus and the address bus. Once the data path is available, you can start thinking about the ASMD chart. Start instruction by instruction, assuming a common initial state where the instruction register is loaded and the program counter is incremented, since these two actions will always be necessary whatever the instruction. Once you have partial ASMD charts for all your instructions, you can put them together to build the complete ASMD chart. The easiest part is now about to start. Once the ASMD chart is available, we can start coding. As usually in the case of FSMD architectures, you might prefer to use a hierarchical structural approach. Create the design files for each block, and then a top-level description to put them all together. Then make sure that you can synthesize the full project without any errors. Once that happens, you will need to create a simulation source file and start the design verification activities, try to represent as many movement situations as reasonably possible, including pen up and pen down, and check if your solution behaves as expected for each one of them. You may realize that exhaustive design verification becomes considerably more difficult, to say the least, in a case like this. When your simulation proves successful, it's time to add the constraints file and generate the bit stream to program the FPGA. You may need to do some wiring as well, so don't forget to get hold of the necessary tools. When the full thing is assembled, give it a go. How can you expand your work? Well, start by considering the first question. Can you draw a circle? Or do you turn right and left by inverting the rotating direction of one of the motors? As a second topic for expanding your work, you may consider automatic actions upon obstacle detection. For example, if the cart hits the wall, move back for a while, turn left, and start moving in front again. I hope that you may have fun during this assignment. Thanks for your attention.